For number 8, we're looking at some measures of variation, how spread out the data is. We're going to find the range and the sample standard deviation. The range is just the difference between the largest number and the smallest number. So you have to identify those two and subtract them from each other. The sample standard deviation is a little more complex to calculate. I'm going to show how to do it quickly in Excel. You can follow the steps and work it out by hand. The steps are listed in the textbook, where you can see them step by step in the Help Me Solve This or view an example. Basically, you're going to be figuring out what the mean is, and then you're pretty much averaging how far away all these data values are from the mean. That's a good way of thinking about what standard deviation is. It's an average of how far the data is spread out from the mean. I'm going to copy this to my clipboard and then put it in Excel. So you can actually get, you could get the min and the maximum if you had a larger data set. And it was hard to make sure you didn't overlook anything. And when you find those two, this is how you find the range. You would take the larger one and minus the smaller one, and that is your range, so largest minus the smallest. The sample standard deviation equals standard deviation dot S, because we have a sample here, and you select your data, close your parentheses, and this is your sample standard deviation for that sample. Number 9 is about being able to visually see larger and smaller standard deviations. So a small standard deviation means the data is more compact, more of the data is closer together in the middle, something like this, as compared to a higher standard deviation where you have more data that's out in the tails far away from the middle. So a situation like that has a higher standard deviation because the data is more spread out. We say there's more dispersion. For question 10 here, we have the weights of 50 different candies here. We need to start by finding the sample standard deviation. So you take the sample of 50. You're going to definitely want to use technology for this. It'll make it a lot quicker. I'm putting them in Excel here, then equals stdev for standard deviation dot S, because we have a sample. And I'm selecting the data. And I'm going to close my parentheses. And here's my sample standard deviation. Always make sure how many spots you should round to. At 2 decimal spots, that's 0.067. Now we have a histogram already created. And we're going to take a look at it. It is roughly bell-shaped. And because it's bell-shaped, we can use what is called the empirical rule. And so bell-shaped, we just means it's higher in the middle, and then it tails off down to the right and left pretty symmetrically, kind of like the shape of what a bell looks like. So taking a look at the empirical rule, what it says is our mean, which is right in the middle, and here's a good picture of what a bell-shaped smooth curve looks like. So higher in the middle and tapers off. So what the empirical rule is saying, in the means in the middle, 68% of data is within 1 standard deviation of the mean. Let's see if I can zoom in a little bit. So you go 1 standard deviation either way, 68% of the data. 2 standard deviations either way, you have 95% of the data. And if you go 3 standard deviations within that range, 3 standard deviations either above or below, you have 99.7% of the data. So what are we talking about when we say standard deviations one way or another? Let's look at this example. Determine with the empirical rule the percentage of candies with weights between 0.7 and 0.98 grams. Now it's telling us what the mean is. The mean is 0.84. So if our standard deviation is 0.07, you can think about it like this. If you're at 0.84 and you go 1 standard deviation above, that means you're adding whatever the standard deviation is. So I'm adding 0.07. That gets me to 0.91. If I go 2 standard deviations above, I'm at 0.98. So 0.98 is 2 standard deviations above the mean. And you can see that if I start at 0.484 and I minus 1 standard deviation, I'm right there. And then I minus the standard deviation again, I'm at 0.7. So this number is 2 standard deviations below, 0.98 is 2 standard deviations above. What the empirical rule is saying is that within 2 standard deviations above and below, there's 95% of the data. So that would be our answer here. 95% of the data is between those two values. For the next part, determining the actual percentage of candies that fall in between those two data values, you would need to actually look back at your original data and count how many fall in between those data values. Now in this example, there's 50 total data values here. There is only one in here that is outside of this range. And I had just seen it. It says right here, 0.99. That's the only one outside. So there's one bigger than it. That means there's 49 within that range. So 49 divided by a total of 50, there's 98% that are in between that data range. And you'll want to do a similar calculations here for E and F. For E's asking not in between two values, but more than 0.91. So again, look at what your particular values are, but 0.91 is 1 standard deviation above our mean here. And I got that by adding the standard deviation to the mean. I add it one time and I get to 0.91. So looking back at the rule, 1 standard deviation above, I can count these percentages and add them together for the empirical rule to see what the percentage is that is more than 1 standard deviation above. And then actually look at the actual data here and see how many values are above 0.91 to get the actual percentage. Number 11 is about the difference between discrete and continuous variables. And discrete are variables that you can count. So if it's a situation where you can say there's either 1, 2, 3, 4, or so on, you can count how many there are. That's discrete. For example, the number of customers at a bank, that has to be a whole number that you can actually count. So that would be discrete. The possible values are that there's 0 customers, or 1 customer, or 2, or so on, the counting numbers. Continuous variables are ones that you're going to calculate by measuring, and there's an infinite number of possibilities it could take on. For example, the square footage of a house. That's something you have to calculate by measuring, and the possibilities can be anything bigger than 0. So all the whole numbers, but also all the decimals and fractions, and every single possibility of any number that's bigger than 0 can be the square footage of a house. Number 12, we're talking about a discrete probability distribution, and it's just a situation when there's a finite countable number of possible outcomes. In this one, the only outcomes are the numbers 1, 2, 3, 4, or 5. And then the probability distribution lists the probability of each of the different outcomes. And so for it to actually be a legitimate probability distribution, these probabilities have to all add up to 1. That's one of the requirements, because that equals 100%. And so the probability distribution should account for every possible outcome that's out there. So all the outcomes put together should equal 100%. The other requirement is that all the probabilities are actual legit probabilities, meaning that they're between 0% and 100%. Or in decimal forms, they're between 0 and 1. You should see no numbers bigger than 1, and you should see no negative numbers or anything less than 0. If both those criteria are met, then we have a legitimate probability distribution. Number 13 feeds off of what I just talked about in number 12. The requirements for a discrete probability distribution is that all these numbers should add up to 1, 100%. So find out what value you would put there to make all of these add together to 1. For number 14 here, we have a probability histogram, and it just shows the possibilities for the number of children that someone can have, and then the probability of each of those possibilities is how high the bar is. And so all this data is about the number of live births that a mother has had. And so just use the information and pay attention closely to what it's asking. So if it's asking about an exact value, like what's the probability that you randomly select someone who is on their fourth live birth, you would go to 4 and see what the probability of a fourth live birth is. If it's asking for 2 of them combined, fourth or fifth, you would add those 2 probabilities together of being either your fourth or your fifth child. If it's more than a certain amount, so sixth or more, you would add the probabilities together of 6, 7, and 8. And then part D here is asking what is the expected, how many live births would you expect a mother to have if you're randomly selecting a mother? Essentially, the way that you calculate the expected value is doing a weighted average. So I've just copied the data from this into Excel. The possible values are 1 through 8, and then the probability of each of the values. So those are listed right here. And then you want to do your weighted average. You want to take each number here, each outcome, and multiply it by its probability. So that's A1 times B1, A2 times B2, and so on all the way down. The reason I use cell references A1 times B1 is because Excel has that nice feature. You can just drag and drop them. Let me really show what I meant here. If I just type A1 times B1 here, and then I drag and drop the corner, each new cell will be A2 times B2, A3 times B3, and so on. So Excel picks up on the pattern you're trying to go for. After you've done all those, multiplied each value by its probability, you just add them together, and that gives you your expected value or the mean of your probability distribution. So in this case, we would expect the value to be 3.11. Rounded to 1 decimal spot, it'd be 3.1. And now a mother can't really have 3.1 children. You can't have a decimal percentage. But what we're saying here is if we had a large group of women that we randomly selected, we would expect the average number of births to be 3.1 if we averaged all their actual number of children they had, if we averaged it together. Number 15, this problem here is asking about investments. And if you look at what it's asking for at the end, it's what is the expected profit from this investment. So again, we're trying to find the expected value of our probability distribution. In this case, there's 3 situations. The economy is either going to grow strongly, grow at a moderate pace, or go into recession. And associated with each of those is your return on your investment, how much you're going to make. So here are your 3 possible outcomes for how much you will make. And then here's the probability associated with each of those outcomes. And just like we did at number 14, to find the expected value for this probability distribution, you're going to take each of the possible outcomes and multiply it by the probability associated with it. If I use drag and drop in Excel, it copies that multiplication down. And so you multiply all those together, and then you sum them up, add them together to get your expected value for this distribution. And so with this company, I would expect to make $6,000. That is the expected value. What that really means, you're either going to make 40,000, make 10,000, or lose 40,000. So you're really not going to get $6,000. But what it means is if a bunch of people invested, and then we asked all of them how much they made, and we took the average of how much they made, taking all the people who made a lot, all the people who lost a lot, and everything in between, it would come out to an average for that group of people, that random group, of $6,000. That is what we would expect.